So the specific service that we're talking about today that the kernel provides as part of the operating system is virtual memory, which is this view of our memory hierarchy that allows programs to work without having to know where things are exactly in the memory hierarchy. So the kernel is going to translate between what's called a virtual address and a physical address. So over here on the left, you can see what machines used to look like, where the CPU directly accessed the physical memory. But now we're going to introduce this layer of indirection where the CPU is dealing with a virtual address, but that gets translated to a physical address before memory is actually accessed. So the goals here are to be able to use main memory as a cache for disks, and also to provide every process with a uniform view of memory. So each process can pretend like it's the only process running on the system, even though clearly that's not going to be the case. And along the way, it's nice because it also protects processes from interfering with each other. So before we go any further, we should define an address space. So an address space is just an ordered set of non-negative integer addresses. And we generally work with linear address spaces, which don't skip any addresses. And so we're going to have two address spaces. We're going to have a virtual address space, and we're going to have a physical address space. And every byte in our program is going to actually have two addresses. Its address in the virtual space, which is generally going to be consistent every time the program runs. And that's how we refer to memory in, for example, y86. The addresses that we use there are the virtual addresses. And then when the program is actually running, those bytes will be stored in particular physical addresses, and the kernel is responsible for maintaining that mapping. So for example, y86 programs have this virtual address space with addresses that range from 0 up to hex 1000, which is big enough for 4 kilobytes. Virtual memory uses what's called fixed size memory partitioning, where it takes these address spaces and it splits them into these fixed sized pages. So the virtual address space is split into virtual pages, and the physical address space is split into physical pages. These pages are generally the same size, and they are usually fairly large, so somewhere on the order of a few kilobytes up to a few megabytes. Virtual memory uses RAM as a cache for pages. So the process can use this consistent virtual or logical addresses, and then the operating system translates these to the physical addresses whenever necessary, using a table for lookup, with some optimizations that we'll talk about in a bit. So we're going to assume that the hardware handles the caches inside of the CPU, and we're going to focus on the interactions between the CPU and main memory and disk. So here's a picture of how this works. So there is a page table that is stored somewhere. Here it's in DRAM. And this is going to be the lookup for all of the virtual addresses. So for each virtual address, it's going to contain the corresponding physical address. So when we need to look something up, we take the virtual address, we use that to look up in the page table, and the page table is going to contain links. Some of those links are going to be to pages that are loaded into DRAM or main memory. But some of those pages may not be loaded. They may be pointing to places on disk or may just be unassigned. And so if we are accessing a page that is not currently loaded into main memory, as we are doing right here, we're going to have to load that page. And this is called a page fault. We went to look for a page and it was not loaded, so we're going to have to load it. Loading from disk is, as we saw, much slower than loading from DRAM. And so this is going to be something that we're going to want to avoid as much as possible. And so generally when we have a page fault, we'll load the page into memory so that the next time we go to access that address, we can just go directly to DRAM after doing our lookup rather than having to load from the disk.